everyone, Chicken Puck here. Whenever you think of quantum computing and circuits, you immediately go to a C0 or an X gate or a Hadamard gate or a controlled phase gate. But eventually a quantum computer has to do something more familiar, arithmetic. So here's a deceptively simple question. How does a quantum computer add two numbers? So on a classical computer, if I wanted to add 5 plus 3, I would get 8. And the computer would do binary arithmetic. In binary, we have 1, 2, 4. We're going to have 1, 0, 1. And then we have for the 3, 0, 1, 1, right? Then we're going to add these two together. So then the 1 and 1 will give us the 0 here. Then we have a carry bit over here. Then we're going to get another 0. Then we have another carry bit over here. Then we're going to get 1 at the end. So this is our final answer. So at each position, we take 2 bits. We can produce a sum bit and then possibly produce another carry. Example, if I want to do 1 plus 1, I will get 1, 0, and this is binary. The sum bit is 0 and the carry bit is 1. And if I had 1 plus 1 plus 1, get 1, 1, where the carry bit is 1 and the sum bit is 1. So a classical computer has circuits designed to perform these very operations. But what makes a quantum adder different? How does it work? So a quantum adder is a quantum circuit that adds two numbers together encoded in quantum registers that has to be reversible. Suppose one quantum register contains A and the other quantum register contains B. So conceptually, we want this relation. But you might ask, why do I need this A here? If the goal is to just add A and B, what is the point of keeping this A here? So hypothetically, if I took out this A and just left A plus B, this is not reversible. Example, if I told you the sum is 5, how would you know what the inputs were? They could be 4 and 1, or 2 and 3, or 5 and 0. So essentially, we've lost information. Quantum gates are required to be unitary. Unitary operations are reversible. So we want to preserve enough information to reverse the calculation. Looking at this transformation, if I wanted to go back, all I would have to do is subtract A from here, right? We could reverse it. So taking the conjugate transpose on this unitary, we reverse this calculation and we go back to the initial input. That's the fundamental idea of a quantum adder. So now, let's actually explain what these kets mean. So if you were to see ket 5, what we're saying is we're writing this shorthand. The 5 is the shorthand for the binary. So given that we are working with 3 qubits, we can write it as this. Similarly, 3 would go to 0, 1, 1. So therefore, 5, 3 really represents 1, 0, 1, and then 0, 1, 1. So the quantum adder will act on these qubits, so the second register will actually contain their sums. And notice I padded this input register with an extra 0 because the output needs 4 bits, so we can just increase the size of this input register. So if this is all that quantum computing did, it would just be a very expensive classical calculator. The important part is that the input does not have to contain a single definite number. Suppose the first register is in a superposition of 1 and 2, and then we're going to add a second register containing 3. Because the adder is a linear quantum operation, it acts on both branches coherently. So let's see what's happening here. So I took our initial psi state and then the second register which had 3 in it. So then we're going to apply U plus. So bringing the U plus inside, we can take out the 1 over square root of 2 and apply the U to the 1 and the 3, and then plus with the U plus on the 2 and 3. And what you notice is that the first register stays the same. However, upon acting with the U plus, the registers here will add, and we'll get 4 here, and then 5 here. And then we're going to bring back in the 1 over square root 2. So now the registers are generally entangled. If the first register is 1, the second contains 4. If the first is 2, the second contains 5. That's quantum arithmetic. We're not just replacing classical transistors with qubits. We're building arithmetic operations that can work coherently on superposition. We're going to go one step further and talk about quantum adder modulo n. For this theorem, instead of just ordinary addition, we're going to wrap around n. Let's use a very simple example. Let's say n equals 7, a equals 3, and b equals 6. Ordinary addition, so adding a and b, we get 6 plus 3, which is 9. And then 9 mod 7 is 2. So 7 into 9 is 1 with remainder 2. Therefore 9 mod 7 is 2. Therefore the 6 and the 3 will go to b plus a mod n, which is 2. And then we're going to go to the a, which is 3. So you might ask, chicken puck, so why does a quantum computer care? Because a quantum register has a finite number of states. The modular math allows us to perform the arithmetic while keeping our values in a bounded range. In Shor's algorithm, we study the function f of x equals b to the x mod n. So without the mod n here, b to the x will get enormous very quickly. 2 to the 3 is 8, but 2 to the 100 is enormous. But because of the modulo n, the answer has to be one of n possible residues. So now we're going to show that the inverse of addition modulo n is subtraction modulo n. So for our earlier example, we have 6 plus 3, which is 9. So we get 2 mod 7. And therefore 2 minus 3 equals 6 mod 7. So u plus mod 7, we go from 6, 3 to 2, 3. And then taking the dagger of this u, we get 6, 3. So nothing was fundamentally destroyed. We can run the computation backwards if you wanted to. And that's exactly what we require from a unitary quantum circuit. So the main takeaway from this video is that a quantum computer doesn't magically know how to do arithmetic. We have to build the arithmetic out of quantum gates. We started with a simple addition here, but because the quantum operations have to be reversible, we have to carefully construct that addition so that we don't destroy any information needed to reverse the computation. We also saw that quantum arithmetic is fundamentally different than classical arithmetic. Our registers can be in a superposition. So a quantum adder can coherently perform addition across multiple branches of a quantum state at once. After that, we introduced the mod n case. And then since we know how to add, we can start to input more complicated arithmetic. So when you see a giant circuit, like example in Shor's algorithm, don't think of it as one mysterious operation. It's a hierarchy. Small reversible quantum gates are combined to perform addition. And then the adders are used to perform multiplication. And then the multipliers are used to construct exponentiation. And then we got to the f of x function, which is at the heart of Shor's algorithm. So in essence, quantum computers are not magic. They're circuits. And those circuits are built one operation at a time. Thank you for watching.